your quiz that we thought was tomorrow is now Wednesday, right? Because of the practicing ACT tomorrow. So. All right. Here's what we're going to do. First thing today, before we talk about something else, we're going to do number 4. This is so on the dimensional analysis slide, there's 3 links, right? We did a couple of problems from that first one. This is the second one. There's 2 problems from this one today. We'll talk about something else. There's a third one that has questions and answers for you. All right. We're going to do 2 problems right here that have to do with density. So your quiz will have 2 or 3 questions that I haven't decided yet.
Teachers, please pardon the interruption. At this time, we need all new students who don't have a Chromebook to go to the library. All new students who don't have a Chromebook, please go to the library. We also need any 9th, 10th, or 11th graders who missed the swap out last week to go to the library with your Chromebook. Any 9th, 10th, or 11th grader who missed the swap out last week, please go to the library with your Chromebook.
Two to 3 questions on a quiz. All right, so quizzes, we try to keep them about 10 to 15 minutes. We don't want to put in all of anything. So a couple of questions, maybe 3 on this one. One of them will be about density, which is going to be like number 4 and number 7. We're about to do. That's one of them. One of them is going to come from that third worksheet that we're not going to get around to in here. Okay, just to see who goes home and does their homework. All right, and then if there's a third one, I'll come up with it. It'll be fairly simple though. On this handout, for example, number 6 and number 10, if you can do those, then you're well versed in this. Okay, so nothing like 6 or 10 on the test, right? If you can do 6 and 10, then you're very good at dimension analysis, and you shouldn't have to worry about anything. Okay? So I would encourage you to try to do number 6 and number 10. Like I said, if you get that, if you can sort that out, then you're good at this. Okay? We're not going to worry about doing that just yet.
I'm saying that one of them would be the third. This is more info like this.
I think so. Is that?
Because I had some questions on some of that stuff. I've got like anagrams, and when I put it in, I got some stuff like 1.2e, -9. I don't know if I should put it in.
That means 1.2 times 10 to the -9. Okay. On your calculator said the E. Go together. So the E stands for times. All right. Let's try this. Mercury has a density of 13.54 grams per milliliter. How many milliliters would 100 grams occupy? Okay. So I'm not, first off, the reason they're putting that decimal right there is to make that be 3 significant figures. I'm not a fan of writing it that way. I think it's confusing. So I think the best way to write the number 100 to 3 significant figures is that way. Some scientific notations. We're all right about that. All right, so that's the measurement that we're starting with. Somebody's got 100 grams of mercury. The important thing about density and why it's so useful to a chemist, and why we're going to make sure we put one on the quiz this week, is that it gets us between mass and volume. If we measure one thing, mass, let's say, and if we know density, we can figure the volume. If we measure the volume of the substance, and we know its density, we can figure the mass. So just you can measure which one everyone is the easiest to measure, like solids would be mass, and liquids would be volume, and then you convert back and forth using density. So it's a fairly common thing to do. All right, so here's how we will do that. We will start with 100 grams of mercury. Okay, and I'm going to use the density to convert that to a measure of volume, specifically milliliters. All right, now do the grams need to go on the top or the bottom of this conversion factor? On the bottom, okay? milliliters on the top. So this density, you can think of it like this: 13.54 grams of mercury equals 1 milliliter. Okay, those are equivalent. Think of it like that. You've got two equivalent values that you can put in a fraction. It will be equivalent to 1 that you can use to do some conversions. That would get the grams to cancel and leave me with milliliters, which is what it asks for. 1 milliliter is 13.54 grams. 100 divided by 13.54 is how much? 7.39. Okay. 3 significant digits, right? So, which part? Okay. 7.39. 100 divided by 13.54. So, again, it helps a lot of people to write that over 1. Okay, so just fractions, right? So you multiply everything on the top, divide by everything on the bottom. Okay. That's what they measured. Okay, so this is just a fact. They didn't measure this. This is just mercury has that density. Okay, so this is the only other number I'm going to give them. So they have 100 grams of it, 100 milliliters. All right. Question else? All right. Number 7. Page. Somebody went and found a gold nugget. On prospecting in the North Woods, Joe found a gold nugget which had a mass density of 19.2 grams per cubic centimeter. So there's the density of gold. He dropped it into water to graduated silver. The water level increased by 15 milliliters. So let's talk about that in just a second. And I tried to do a little makeshift demonstration first period. We got terrible numbers, so I'm not even going to fool with that right now. But I will show you what a graduated cylinder is, in case you don't know. Here it is. Okay, so this is a graduated cylinder. All right, it's a cylinder, right? Obviously, it's graduated, meaning that it's got measurement marks on the side of it, okay, in milliliters, all right? So it's marked off every milliliter, so we can estimate the 1/10 of a milliliter. So this does a decent job of measuring volume to a 1/10 of a milliliter. It's not too bad. Okay, this is a graduated cylinder. What the guy here is doing is trying to measure his gold nugget. If you put some water, if you put water in one, okay, and then you drop it, you measure the volume of the water. If I drop an object in here, what's going to happen to the water level? It's going to rise, right? It will rise by the exact same volume as the object you dropped in. Okay, so it's an easy little way to measure the volume of something that's not symmetrical, like a gold nugget. That's like picking up a rock, right? It's not going to be square, cube. It's not going to be a cube. It's not going to be a sphere. It's not going to be any of those things. Okay, it's just going to be this shape, this random object. And that's a good way to do it. So that's what they did. They had some water in a graduated cylinder, took the little gold nugget, dropped it in there, and whatever the water level raised, they measured it. And apparently, it was 15 milliliters. So that means this gold nugget has a volume of 15 milliliters. know how many grams. Okay? Now, milliliters and cubic centimeters, how are they related? Yes, no. Then same thing, right? So a cubic centimeter, like that, cube, and milliliter are the same thing. Okay? Back to that SI units page. Okay? So the difference in their use is that milliliters are often usually used to measure liquids, while cubic centimeters are dealing with solids. So we took a solid piece of gold and dropped it in some liquid water, right? So liquid water changes measured in milliliters. And since a milliliter and a cubic centimeter are the same thing, then we know cubic centimeters of a piece of gold. Follow that? Okay. So just a little fun fact to always remember: milliliter and cubic centimeter are the same. So densities get reported in either or, usually depending on whether it's a liquid or a solid. Okay. So 15 milliliters is our measurement that we took. We want to convert that to grams using this density. The first thing we need to do is get rid of the milliliters, get cubic centimeters. The next thing we need to do is get rid of the cubic centimeters, get the grams. Okay. So cubic centimeters cancel, milliliters cancel. We just said cubic centimeters and milliliters are the same thing, so 1 to 1. According to our information here, there are 19.2 grams of gold in every cubic centimeter. So this tells us the grams of gold. So 15 times 19.2. Pretty significant digits, is how much. You ready, Ed? You ready, Ed? But why would this guy want to know the mass of this gold, baby? Worth for selling by, right? So gold is valued by its weight. Grams or ounces, depending on where you are. All right. Questions? All right, so there's two examples of density. One going from grams, the first question went from mass to volume, this one from volume to mass. Okay. The only difference is really is the density is inverted. Questions together. So one question on Wednesday about density, one question from the third link there, and possibly or probably a third question. All right. Let's see. All right, so y'all got ACT practice tomorrow. You got a quiz on dimension analysis Wednesday. Today we're going to talk about atoms, ions, molecules. We're just going to talk about terminology, really. Okay. So it's repetitive. Most of it you've probably heard before. Some of it's kind of simple. Doesn't bore you. All of this will be elaborated on in the next weeks and months. So probably around by the end of October, we will have elaborated on all this stuff in ways that are way more complicated, probably way more interesting, but also way more confusing than what we're going to talk about today. Still in the simple stuff. Ain't got hard yet. couple of weeks, we're talking about walking through walls, and you're not even sitting here, all that good stuff. Or you might not be sitting here. Maybe you are, maybe not. I don't know. Get into that in just a few weeks. Along those lines will be blown. You're welcome to try. A kid tried one day in class, busted his nose, blood running down his face, his back. Yeah, he tried, he took a shot at it. I mean, I didn't tell him to. He didn't even announce that's what he was going to do. We were discussing the concept, and he just got up, and walked into the wall, let it in front of his nose. I said, "What are you doing, man?" He said, "I just want to see if it was my lucky day." Strange people in this world. He walked. He didn't run into the wall, but he was a pretty brisk walk, and he did not let up. Like he just walked into it.
Well, that would be a crazy story to tell if he actually did go to the wall.
Well, we would have had a story to tell. So not to get a month ahead of ourselves, 2 weeks ahead of ourselves, but it is possible to walk through a wall. There's only one recorded incident of it ever happened, so don't like your chances. No, you just have to line all your atoms and particles up with the atoms and particles in the wall. If your particles line up with the particles in the wall just perfectly so that your 90% empty spaces are in alignment, then you'll just pass right through the wall. Anybody know the story when it really happened? Anybody ever read it? Jesus did it. Walked through a door. Post-resurrection. So, messing with his creation a little bit. So, walk through a door. So, not to get on a complete tangent here, but we'll bring this kind of stuff up off and on throughout the year. So, people call things like that miracles, right? It's not really a miracle, it's a manipulation of science. Because it's physically possible to do it. So, is it a miracle or not? Raising people from the dead, that's a miracle, right? Walking through a wall, yeah. You created physics, you walk through a wall, it's not a big deal. Didn't break any rules. Miracles have to break the laws of science. Walking through a door didn't break the law of science. Anyway, I digress. Another day, another time. All right, here we go. Quick stuff. Elements. Okay, what is an element? It's pure substance. Okay, so the purest of the pure substances. Okay, so these are the simpler. They cannot be separated into simpler substances. So if you take a pure piece of aluminum and you just keep shredding, if this was physically possible, which it's not for a human to physically keep shredding that down to an atom, get it down to one atom, right? You still got aluminum. If you split that atom apart, you don't have aluminum. Now you've got two atoms of something else. Okay. You also have an enormous amount of energy released. Okay. All right. So at that point, though, you're doing physics and not chemistry. So as soon as we split atoms, we've left chemistry and gone to nuclear physics. So we don't cross that line in here. Well, we could. I mean, we could. It's a thing, right? Nuclear fission. So we split uranium atoms all the time, generate electricity. And we split them to blow stuff up too. Ain't done that in a while. Some people still do it. Certainly have the means to.
Can we make a particle accelerator?
No, I mean, in theory, I guess, but we're short, I don't know, a couple $1 billion equipment. We'll come up on short. We can take up donations if y'all want to. GoFundMe. It's a $5 billion goal. Particle accelerator on a high speed chemistry. We don't have enough room either. It takes like the big ones are like 2 miles wide. You gotta have a ginormous place. But usually on the ground. But, yeah, the thing. And we run the risk of blowing something up. Or one really strange theory of creating some kind of wormhole in the universe that was always been avoided too sometimes. I don't buy that. I don't buy that as a possibility. I do buy obviously it's a possibility that we blow its way up, so we probably need to steer away from that.
More like we can write a campaign, get your offense to ultimate riches. Like,
Yeah.
just like that.
Try that. That's not been done by anybody who wasn't GCC, so. You can try that. The problem is you gotta make sure you can go and get back. All right, if you look at that periodic table, like that, give y'all a periodic table like first day of class, right? So if you take a look at that right quick, and starting tomorrow and probably every day thereafter, you're gonna, when you get to class, just get out your periodic table in your calculator and be ready to go, because we'll probably use it pretty much every day for the next rest of the semester. If you take a glance at it, again, yours is a little bit incomplete, it's old. It's not that big a deal, but if you look at the blank space in the bottom right-hand corner, that's been filled up. They've synthesized the rest of those in the last 10 or 15 years or so. We're up to number 118 now, which would go right underneath radon in the last column. Not that big of a deal to a chemist because none of those are all highly radioactive and unstable, which means they don't stay around long enough to make chemical compounds. So that's more of a physicist thing anyway. We deal most primarily with the first 92, the ones that occur naturally and therefore are stable enough to form chemical compounds. Other than that, chemists don't get overly interested in the rest of them. They're interesting, but they don't have a lot of practical use. With the exception of maybe plutonium, whose only practical use is to make nuclear weapons, which is practical, but frowned upon in high school classes. We start building weapons, we're going to get in trouble. But if we have a particle accelerator, we could in theory enrich some uranium. See how it goes.
I'm down if you're down.
I mean, you know, go up with the money and talk about it.
Then we can get
What?
like,
Where do you buy that stuff? I don't know. We have to just manufacture. I guess we're getting an egg.
and then we can get
I guess
like.
we get Lipscomb and Whaley on this project.
You get like
I
little.
need some tubing, I need some metal tubes that are about 6 miles long with a certain. Put that up for us back there. All right. So other elements are synthetic. Most of those are radioactive. Here's an important term. We're going to come back to this term in a minute. But ions. Okay, an ion is contains an imbalance of protons and electrons. So remember that definition in a minute when we discuss what a proton and electron actually is. We'll come to that here in just a second. Compounds are when we take two or more of those things on the periodic table, those elements, and we chemically combine them, and we'll define that a little further in a few slides too. All right, but we're going to bond them together. There's some type of interaction with electrons. Infinite possibilities. There's no limit to the number of compounds. I don't know how many have been identified. The last I heard 20 years ago, hundreds of billions of known identified compounds. There's an infinite number of possibilities. There are hundreds of thousands a year that are created, if not more than that, in laboratories that have not been created before. It's not that hard to do. So there's no limit on that. Compounds can be broken down into simpler substances. You can decompose a compound into another compound or to its what we call its constituent elements. Like for example, water, H2O, can be decomposed into hydrogen and oxygen. Hydrogen and oxygen are its constituent elements. All right, so we defined element already. So let's talk about an atom for a second. It's the fundamental unit of an element. And it has three parts, which y'all learned this in like elementary school. Okay, there's three parts to an atom: proton, neutron, electron. Okay, Protons have a positive charge, electrons have a negative charge. Neutrons are neutral, meaning they don't have a charge. Which of those two are found in the nucleus of an atom? Protons and neutrons. Y'all probably drew pictures of that in elementary school. Pictures were all wrong. That's okay. The electrons are found outside the nucleus. We will discuss, I won't say specifically where, because we can't know specifically where. We will discuss where we think they are in a couple of weeks. 90% probability. Protons and electrons are the most important to a chemist. The protons are going to tell us what atom we have, what element we have, I should say. The electrons are going to determine how that atom is going to chemically or not chemically interact with other atoms around it. So protons and electrons are where we concentrate. Neutrons, for the purposes of chemistry, just provide mass. Okay? Now, to a physicist, they're important. But to a chemist, neutrons are just sources of mass. Okay? They don't determine the chemical properties or behaviors of the substance. So we're not too interested in them. All right, so we already defined an ion, an atom with an imbalance of protons and electrons. So a neutral atom is going to have the same number of protons and electrons. Let's take carbon, for example. If you look at your periodic table, carbon is number what? It's number 6. It has 6 protons. We'll see those things in a minute. If it's a neutral carbon atom, it's also got 6 electrons. Just as many positives as negatives. If that number gets imbalanced, so if you have 5 electrons or 7 electrons, now you have an ion. An isotope, which we will discuss a little bit more Wednesday, I don't want to say tomorrow, I won't be here tomorrow, but Wednesday, are 2 atoms that have the same protons, but they've got different numbers of neutrons. So they're the same element, they just weigh a different amount. Okay. All right. Atomic number. So now look at your periodic table. Okay. Each little box on your periodic table has 2 numbers, a symbol, and a name. Correct? Symbol and name, pretty self-explanatory. What about the 2 numbers? Well, the whole number, the one at the top, but if you look there, everything's ordered 1, 2, 3, 4, 5, all the way to 118. That whole number is the atomic number, which is the number of protons. That's very important. Okay, to recognize that that's the number of protons, and if the atom is neutral, it will also be the number of electrons. That's very, very useful. A mass number is how many neutrons are in a single atom. So that's not on the periodic table. That second number there is not the mass number. A mass number only applies to a single atom. Different atoms of the same element can have different masses. But the second number you see on the periodic table is the average of all the mass numbers of all the atoms that exist in that sample. That's called the average atomic mass. So the periodic table has the atomic number and the average atomic mass. In a couple, 3 months, we will redefine average atomic mass into a much more useful thing. But not today. All right, when we talk about the charge of an atom, it's the difference in numbers of protons and electrons. You get too many electrons, you have a negative charge. You get not enough electrons, you got a positive charge. What time are we getting out of here? Oh, okay. We're doing good. All right, here's some models. These are not pictures of atoms. Okay, we can't take a picture of an atom, at least not with visible light. Visible light doesn't interact with the nucleus of an atom. It's too small. The atom is too small. So visible light pictures don't do us any good. So we have to make models of things. Okay, so we're making some models here, and we're representing protons and neutrons as these spheres. Okay, so these are 3 different carbon atom nuclei. Notice that they all have 6 protons each. Okay, because if they didn't, they wouldn't be carbon. If they had 5, they'd be boron. If they had 7, they'd be nitrogen. any other number, they'd be whatever number it is on the table. So to be an atom of carbon, you gotta have 6 protons. But an atom of carbon can have different numbers of neutrons. Most carbon atoms have 6 neutrons. In fact, it's about 98.9% of them do. They have 6 neutrons. That would give this carbon atom a mass number of 12. So we call it carbon 12. 1%, 1.1, whatever, close enough, 1% of carbon atoms have 7 neutrons. So 6 plus 7 is how much? 13. So that gives this carbon atom a mass number of 13. This one's got a mass number of 14, which means it has how many neutrons? 8. 14 minus 6 is 8. Okay. So, but notice these percentages, 98.9, 1.1, and less than 0.1. If you take the weighted average of all of these, which is what we will do Wednesday after the quiz, take the weighted average of all of that, what you're going to get is 12.01. So look at your periodic table and see if in the carbon box, if it doesn't, under the 6, if it doesn't say 12.01, right? Okay. So that's the weighted average of all the isotopes of carbon. More on that Wednesday. Okay. 2 different ways to write the same thing right here. If you're handwriting something, this is pretty much the easiest way, but this is annoying to type. It's a superscript 12 with a C, that means carbon 12. 13C means carbon 13. 14C means carbon 14. If that's a superscript, that's a little annoying to type. You got to hit a couple extra buttons to make that font go up like that. Okay. So if you're typing, like if I'm typing your test, it's much easier normally to just type it carbon-12, carbon-13, carbon-14. It's easier to do. They mean the exact same thing. All carbon atoms have 6 protons. So if you have a mass number of 12, that means you got 6 neutrons. If your mass number is 13, you got 7. If your mass number is 14, you got 8, so on and so forth. Okay. So top left-hand corner is where we would put the mass number. Top right-hand corner is where we would put the charge. So for example, a chlorine atom with 17 protons, because it's number 17 on the table, and 18 electrons has a charge of 1 minus. Goes right there. Oxygen, 8 protons with 10 electrons would be 2 minus. Nitrogen has 7 and 10 would be 3 minus. We're going to write that superscripted in the top right corner. Same thing if it's positive, still goes in the top right corner, it just has plus sign instead of a minus sign. Sodium's got 11 protons, if it only has 10 electrons, then it's plus 1. Beryllium atom has 4 protons. If it's missing 2 electrons, it's 2 plus. Aluminum, 13 protons, if it's missing 3 electrons, would be 3 plus. Here's a more combined way to do it. Okay, there's 2 different elements. One is a neutral atom, and one has a charge. So here's how we can read this. This is hydrogen 3, also known as tritium. But hydrogen is an isotope of hydrogen that has a mass number of 3. The atomic number of hydrogen is 1. So that means we have 1 proton and 2 neutrons. Now, how did I get the number 2? 3 minus 1, right? Because the mass number is protons and neutrons. And the atomic number is protons. So if I subtract atomic number from mass number, I'm left with just what? Neutrons, right? Okay. Since there's nothing right here, it means it's neutral, which means 1 proton and 1 electron. Over here, we have a 2 plus, right? So 12 protons and a 2 plus charge means how many electrons would we have? It's either 10 or 14. Which one is it? So you have more or less electrons than protons if you have a positive charge. You got less, right? Do you think it's 10 or 14? 10. Okay. So magnesium atom has 12 protons, that number right there. This particular magnesium atom only has 10 electrons. That number is telling me that. How many neutrons does this magnesium atom have? 12. 24 minus 12 is 12. All right, very common symbol, very common way to write this stuff, except normally we don't put this number down here, okay? This 1 or this 12 is normally not written because it's usually, I always assume that a chemistry student like you or a teacher or a chemist somewhere has a periodic table in front of them all the time. So I can find that number, right? I find the big H on the table and I see that it's number 1, correct? I find Mg, I see it's number 12. So that number that's being a little bit redundant to put the atomic number in the symbol because we operate as if everybody's got a periodic table handy enough to go find that number. Getting close to done here for today. All right, definition of a compound again, a substance that consists of a combination of elements. They're held together by a chemical bond, which is an attraction between atoms resulting from some type of electron interaction. There are 2 main types. The world is really not this simple, but there are 2 main types. An ionic bond is an attraction due to the exchange of electrons. A covalent bond is attraction due to the sharing of electrons. First period said they'd heard that before. How about y'all? Exchanging electrons versus sharing electrons, right? Very good. A molecule is the fundamental unit of a covalent bond. So when a covalent bond forms, you've created a molecule. When an ionic bond forms, you've created a crystal lattice. So the word molecule does not apply to ionic compounds, only to covalent compounds. An ionic compound exists in a structure called a crystal lattice. We will discuss much more of that in about October or so. Oh, that's good. All right, before you get back in here Wednesday, so next class meeting is Wednesday. Watch this video. It's about isotopes. Be ready to take a quiz on dimensional analysis. That shouldn't say tomorrow. That should say Wednesday, but whatever. Tomorrow is Wednesday. Now, I'll give you all the conversion factors. I'll even give you the time, just in case somebody doesn't know how many hours in a day or something. Sure we have. Everybody on. All right, camera's off now.